standard solution format of damped harmonic oscillator. So the genetic definition of damped harmonic oscillator is the system harmonic oscillator system with some friction. So if there's some kind of force existing on the system internally, but that's produced some sort of resistance proportional to velocity of the object, then you can find the solution of that simple harmonic oscillation with the damping with this format. So one of typical example is a string with the mass m, which attached to the cylindrical portion of the bar with attached to the mass m, the string constant k, and that cylinder part submerged into some sort of liquid in the beaker, and that liquid have some sort of viscosity which produce that some sort of frictional force against the motion of this object. So this mass m subject to the gravity downward, and also there's spring force based on Hooke's law, that the spring force always pointing that the center of equilibrium position, the middle actually center of the vertical direction. So also the viscosity produce the frictional force, which is proportional to the velocity of this object, which is minus b times velocity v, which is minus b y over dt. So you plug all the forces into the simple formula of the Newtonian system, and the damping force itself is minus b times velocity v, which is v dy over dt. And also maybe you can think of this original direction as x, so that should be x. And so basically the spring force plus damping force should be main part of Newtonian system, which is mass times acceleration. So that is m times d to x over dt x. So you plugged all the force into here, and that your basic formula of this damping harmonic oscillator description is mass times d to x over dt square plus b dx over dt plus kx equals 0. And its solution is already well known from the second order differential equation. So the x of amplitude of displacement of this mass m is maximum amplitude times exponential function to the power of gamma t times cosine omega prime t plus pi. Here's the gamma is damping factor, which is function of b over 2m. The velocity viscosity constant divided by the mass, and resonance frequency, angular frequency of system omega prime is square root of k over m minus b square of 4m square. So that is solution of this damped harmonic oscillator. So I gave you some typical examples, but any system could be damped harmonic oscillation as long as the amplitude decays in time proportional to the exponential function. So if you plot this amplitude in time, then it should be like this. This is time. This is the amplitude x, which is a function of t. So Obviously, because of this is a harmonic oscillator, their amplitude should be like this, like this. They're oscillating in time, but at the same time, the amplitude, this is, if there's no change of maximum amplitude, then this is just simple harmonic oscillator. But as you can see, this amplitude itself contains the exponentially decaying function. So if you plug that exponential function, that amplitude should be exponentially decaying, like this. So if you replot envelope of this amplitude, then it should be like this. So this basic amplitude of this function is proportional to exponential function. So this one is proportional exponential gamma t. So that is typical pattern of damped harmonic oscillation, but its behavior is pretty much depend on the relative scale between the first term and the second term inside this square root. So k over m and the b square over 4m squared. So the behavior of this simple harmonic oscillator with the damping is pretty much dictated by the relative scale between these two terms. So number one, let me rewrite it. So number one, if damping is really large, so large, which means your first term, the second term, b squared is much bigger than 4mk, then your plot of this amplitude will be like this. There's no oscillation, just quickly converts into the minimum amplitude. So this is C. This is called overdamping. But if this so then second case, if b squared, the second term, the numerator of b squared. Oh, let me just rewrite this equation, then you can more easily understand. So if you take k over m out of this one and k over m, then that is 1 minus b squared m over k over m squared, right? And if you rewrite it, then that should be k over m times 1 minus b squared. This should be 4 too. That's 4. 4 mk, right? So that is omega prime. So here, there's one thing I want to tell you. Square root of k over m, what is that? You remember what square root of k over m is?
Omega.
Yeah, omega of angular frequency of simple harmonic oscillator without damping. So the angular frequency of damped harmonic oscillator could be expressed with the simple harmonic oscillator without damping and damping term. So if you rewrite it, this one could be omega prime, could be omega times 1 minus b squared of 4 mk. So basically, if you find out which one is bigger, so like numerator is bigger than the denominator or denominator is bigger than numerator, you can find out that this square root term is going to be the real number, 0, or imaginary number. So if it is imaginary number, then you have like more oscillating, and if it is just like a real number, then it will be just damped harmonic oscillator behavior. And if it's zero, then there's no angular frequency. There's nothing. There's no oscillating. So let me just plot that the amplitude of this damped harmonic oscillator, uh, in with the relationship between the b square and the 4mk. All right. So let me rewrite it. Here's omega. Oh, hold on. Omega prime angular frequency of damped harmonic oscillators is omega times 1 minus b squared of 4mk. So as I said, number one, if the b squared is much larger than 4mk, then the this inside of this number will be the minus. So this omega prime will be the imaginary number. Okay, so that makes this t, and the x of t becomes like this. So that's ckc. So this, let me just do. Then number two, if that is called the overdamping. And if b squared is smaller than 4mk, then this inside of this square root will be a positive number, right? Because the second term is smaller than 1, and 1 minus the whatever number is smaller than 1 will be the positive. So the square root will be the real number. So that make omega prime the real number. So that is called underdamping, because your amplitude have several a few oscillation before it just comes to the rest. So it will be like this. This is T, and that will be like this. Swing a few times and comes to the last. So then following the just typical pattern of simple harmonic oscillator, if the b square is smaller than the 4mk. And number three, if b square is same as the 4mk, then inside of square root will be 0. So that means omega prime will be the 0. Then this is called the critical damping. And in that case, there's no oscillation, no, per like a plus minus back and forth, up and down motion of the amplitude. There's absolutely zero oscillation. So that will be like this. Okay, so the T and X. So if you plot all three different patterns of damping, damped harmonic oscillator, and its amplitude in time, then that will be like this. If this one C, this one is A, and this one is maybe B, then will be like this. This will be this T, and this is amplitude, and the C will be like this. C, and A will be like this, and B will be like this. So this is A. So A has a few swings until the amplitude comes to the rest, and C is quickly just comes to the 0, and the B will be the just continuous. There's no oscillation, plus minus sign, up and down motion. So the this case, the critical damping, the amplitude is reached. I mean, so like this amplitude reach equilibrium in the shortest time. So that's quickly just come down to the rest without any oscillation. So that if the um, the viscosity of frictional term is same as the mass times the spring constant multiplied by 4, then that is conditioned to create the system quickly just reach the equilibrium and stay in the make that the system actually stay in the static motion without any up and down kind of like oscillating pattern. So that is typical solution for damped harmonic oscillation. And then we're going to move on to the forced harmonic oscillation with the external force. Before we moving to the next one, do you have any question regarding the damped harmonic oscillator?
No.
Okay. So once you quickly finish up all the detailed topics of the different kinds of harmonic oscillator, I'll show you a video for sample problems, and you will have a chance to actually find out how those solutions can be used to solve the problem too.
Mm-hmm.
So next one is forced oscillation, forced harmonic oscillation. So that's called forced harmonic oscillation. So up to now, there's two different kinds of oscillator. There's simple harmonic oscillator and the damped harmonic oscillator. But we assume there already existing force inside of this system. So there's even before we actually consider that the motion of the harmonic oscillator, I assume that there's the force produced that the oscillation motion, like a perturbation of the system. But that's a little bit unnatural because without the external force, there shouldn't be any existing energy source provide that continuous power into the system. So there gotta be some kind of like external force continuously compensate the energy loss out of the friction and energy loss, right? So in case that there's existing external force, external power source continuously provide the energy into the system, and then simple harmonic oscillator continuously gain the energy from the external energy source. So if there's external power source provided to the system, and the system is gaining the energy, it is called the forced harmonic oscillator. So that's more actually practical, realistic case of harmonic oscillator, because without the external source, it's absurd that the system is continuously actually running. So we have to set up some sort of energy source producing the power into the system. So this is like a typical simplified configuration of simple harmonic oscillation. So you have system, and without just imagine you have some kind of like a toy, but if you don't have battery plugged in, obviously a toy will not gonna just run, right? So you have to provide the external force, which is probably battery. So if you plug that battery into the system has continuous movement and motion. So this external force part is called external power or external force. Make the system continuously run. So usually in physical system, external force is functionalized with the sinusoidal or sine function or cosine function, just like solution form of simple harmonic oscillation. So usually the external force itself is proportional to the cosine omega t. They also external force usually assumed to have the the force term with the cosine function and sine function. So system may have external force applied to it that has its own particular frequency. So this is specific frequency of external force. This omega has nothing to do with the internal and frequency of the system frequency. So that has separate frequency itself, omega naught. So this is a simple harmonic oscillator or damped harmonic oscillator, and their frequency itself determined by K or M or B, as I already showed you in the previous topics. But this omega is arbitrary parameter of external force. So you can actually just determine what frequency is given in that external force. So you can set up omega as you want. So it has nothing to do with the internal angular frequency of system. So if you plug that into this Newtonian system, so now you have m times a, which is the overall system force under the Newtonian system. That is kx minus bu damping term, and that is, if there's no external force, then that should be same as zero, as I already showed you the previous damped harmonic oscillation. But now we plug external power source into this system, so that should be f naught cosine omega naught, omega t. Okay, is so net force itself is no longer zero, because there's continuous force energy flows into this system. So if you just re-express this whole formula with the full second order differential equation, then that should be m a. You moved this one to left hand side, this formula, then that should be ma plus dx plus bu equals f naught cosine omega t. That is basic format of forced harmonic oscillator. Here, this system itself, as I already showed you, characterized by the spring constant K and damping parameter B and the mass of the object inside the system. So omega naught, as I already show you, that is function of two basic parameters, square root of K over M, in case that you don't have like damping term, but that is different from the omega of external force. So if you re-express this harmonic oscillator equation, then that should be m d2x or dt squared plus b and dx over dt plus kx equals f naught cosine omega t. Okay, so usually in case you have external force, the solution of this type of second order differential equation is given by the format of sine function. So that should be x times maximum amplitude times sine omega t plus initial phase pi naught. So let's plug this simple solution format of this forced harmonic oscillator back into this formula, so you can find the relationship between x maximum amplitude and omega and pi naught. Okay, so if you plug that, then maximum amplitude itself, hold on a second. Yeah, maximum amplitude itself is to be function of f naught over square root m times omega square minus omega naught square of square plus b square omega square of m square. That is the expression of maximum amplitude of this simple harmonic, I mean the forced harmonic oscillator. And the initial phase f, pi naught also could be expressed with this system parameter. So pi naught initial phase is arctangent of omega naught square of omega square over omega times b over m. That is the solution of pi. So if you plug this into this formula, you will find this relationship. So depending on the system parameter, you can actually quantify how this forced harmonic oscillator behave with respect to the external perturbation, external force. Okay, so let me give you that description of how the system actually respond to the external force. So did you complete? Did you
Yeah.
summarize? Okay. So now, if you plot the amplitude in terms of frequency, so now you said you have like the graph. You plot the amplitude of the system. That could be maybe x. And now this is omega. So you plot amplitude in terms of the omega, external angular frequency. That is frequency, angular frequency of external force. So you can control this omega. You can put the 1, you can put the 10, you can put the 100. So this is like a parameter of your control. So if you just change that omega of external force, you gradually change. And at some point, that omega will meet the omega naught, which is characteristic frequency, angular frequency, or system angular frequency. So you just gradually change that this external omega, the angular frequency of the external force, and amplitude will gradually just increase like this. When this omega is exactly same as omega naught, then you will have a maximum amplitude. Just take a look at this formula. So if omega is same as omega naught, then first term of the square inside the square root equals 0, and only have second term. So because of the first term is 0, this inside of the square root will be the minimized, then make this whole amplitude maximized. Okay, so now I plot actually this equation, x amplitude with respect to the omega. Okay, so I just plot it right there. So this is actually x m. So then amplitude is just maximized when omega is same as omega naught. So that is called resonance. And resonance, if the damping is negligibly small, most of external force or energy out of the external energy source is 100% transferred to the system. So now you have 100 joule out of external force and plug that into the system. And with the system that has intrinsic angular frequency is maybe like 10 hertz with the 2 pi 10 hertz. Then if you just change the frequency of this external force with the 10 hertz, same as the system frequency or characteristic frequency, 2 pi 10 hertz, then this 100 joule, in principle, if there's no damping or damping is negligible small, this 100 joule supposed to be transferred to the system into the system without any energy loss. So system must have 100 joule too. So there's no energy loss. It's called the resonance. Okay. Resonance is very unique physical phenomena. In a lot of cases, natural examples have this kind of phenomena. One of the good example, I don't know if you heard that this news, some bridge, they just suddenly collapsed while this wind actually started hitting the bridge for some time being. So that tune of that bridge actually just swung by the like wind for some time, and it turned out that the frequency of wind is exactly same as system frequency of this bridge, so that all of the energy of the wind just plug into or transfer to the bridge, and finally the amplitude becomes bigger and bigger and bigger and bigger. At some point it just starts beyond the structural threshold and just bridges suddenly collapse. And maybe you saw that the news, um, the earthquake, happened some time ago, and so suddenly the buildings, start collapsing because the frequency of the earthquake is exactly same as the intrinsic frequency of the buildings, and the building just collapsed even with a small, amplitude of earthquake. So that is similar kind of phenomena that's called a resonance. So resonance can create some kind of a catastrophic failure or catastrophic, problems of the system, or vice versa. That also create a large amount of energy transfer. So the sharpness of this resonance peak, it depends on the also system parameter. So if damping is big, then this resonance peak is kind of like a less sharp. But damping is small, then when this resonance, when your angular frequency getting close to this system frequency, then they have sharper amplitude and make this resonance amplitude much bigger. So how this system respond to external force is pretty much depend on the scale of damping. So damping is not negligible, and that creates a huge amount of energy loss. Then even at the resonance, your amplitude itself is gonna be the much smaller, but reach out that resonance pattern reach out the broad spectrum of omega angular frequency. But um, damping is negligibly small and there's no damping, then that's the angular frequency of external force exactly match, then amplitude is overshooting like this. But it only happened when omega external angular frequency exactly match with the characteristic or system frequency. So the quantity indicating that the sharpness of this resonance peak is called Q value, or quality vector, quality value. Hold on. Quality value or Q factor of resonance system. This Q value usually or Q factor is defined by m times mass of the object times system angular frequency divided by damping term. Or it also defined by system angular frequency divided by bandwidth of this plot. So you can actually define bandwidth. Okay, hold on, let me change that color. The color. So you take a half of the maximum amplitude and draw the straight line, and there will be 2 points will meet with this graph, right? And the width between the lowest, lower frequency and higher frequency, the space between those frequency is called the bandwidth. So your quality factor Q is normally defined by resonance frequency divided by bandwidth. Sometimes we use this kind of definition to define the Q vector. Or if you already know system parameter, you can use this definition too, m times omega naught over b. But they also is indicating that the quality of the resonance. If Q is low, which means the bandwidth is wide, then your resonance peak is like this, resonance. But if Q is high, which means bandwidth is delta omega is small, then you end up with really sharp resonance like this. So that's why the Q is called the quality factor, because that indicating how sharp that resonance peak is in given system. Okay, so that is like end of this chapter in the main part. Do you have any question?
No.
So the three different harmonic oscillators. First, simple harmonic oscillator without the external force, without the external damping, internal damping actually. And damped harmonic oscillator with the damping term, which is produced by the frictional internal force. So damping itself create some kind of resistive, energy, prevent the system from the continuously actually oscillating. So if there's a damping, the system will just come to rest at some point. And the external force, the harmonic oscillator, is there's some kind of external energy source produce and provide the continuous energy into the system. So then make system is just keep on going, running, okay, until this external force is taken off the system. All right. So hopefully you memorize all those three different types of harmonic oscillators. And if you don't have a question, let's move on to the sample problems. Okay, let me switch that. This first one thing. Okay.
Okay, example 14-2, car springs again. Determine the period and frequency of the car in example 14-1A after hitting the bump. Assume the shock observers are poor, so the car really oscillates up and down. So in order to solve this problem, we have to take a look back. Example 14-2, 14-1. So the 14-1, let me just read that problem for you. Car springs. When a family of four with a total mass of 200 kilogram step into their 1200 kilogram car, the car springs compress 3 centimeter. First question, what is the spring constant of the car springs, assuming they act as a single spring? B, how far will the car lower if loaded with a 300 kilogram rather than 20 kilogram? So let me give you the condition of this problem first, and then I'll solve some of the 14-1 problem to solve the 14-2. So family mass, as I already mentioned, family mass, total mass. Family's total mass is 1200 kilogram, and the mass of the car is 1200 kilogram. So the total mass of the family and the car is 1400 kilogram. So the weight of this car with the family should be the mg, mass times gravitational constant, acceleration constant value. So that is mg. That is weight, which is 1400 kilogram times 9.8 meter per square second. That is 1960 Newton. So now we have to, so now the compression length is also one of the conditions. Compression length is 3 centimeter. From that, we can actually figure out the spring constant. The maximum compression length is 3 centimeter with this amount of force. So based on the Hooke's law, force of spring is E minus AX. Here K is spring constant. X is the displacement or deformation or compression of the spring. The minus sign is only just indicator of direction of force, so you don't have to worry about it. So K value should be force divided by X, displacement of the spring. So the total amount of force applied to this spring is 1960 Newton, and that force creates 3 centimeter displacement, so that is 3 times 10 to the minus 2 meter. From that, spring constant should be 6.5 times 10 to the 4 Newton per meter. So as you remember, period T is defined by 2 pi times square root mass over spring constant K for the simple harmonic oscillator with the spring. So that is mass family, and this is spring constant we just got from this Hooke's law. So if you plug numbers into this formula, then period should be 2 pi square root 1400 kilogram, and the 6.5 times 10 to the 4 Newton per meter. So from that, the period should be 0.92 second. All right. And as you know, the frequency is the inverse relationship with the period. So that is 1 over 0.92 second, which corresponds to 1.09 hertz. Okay. That's the answer for this example.
Okay, Tatiana, do you have any question for this first sample problem? That's pretty straightforward. Just plug the number into the given formula. So then if you don't have a question, then let's move on to the second sample problem. Hold on a second. I want to just turn off that. All right, let's move on to the second example.
Okay, then the example 14-3, the vibrating floor. The large motor in a factory causes the floor to vibrate at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3 millimeter. So we gotta just estimate the maximum acceleration of the floor near the motor. So angular frequency omega is the 2 pi times frequency. Now the frequency here is 10 hertz. So that's 2 pi times 10 hertz. So that is 62.8 radian per second. And now from that, you can estimate the maximum amplitude of acceleration. So you remember that acceleration is omega square of amplitude A. That is, this A is maximum magnitude of the displacement of the simple harmonic oscillator. And then this is omega we just got from first question. And if you square that omega and multiply by maximum magnitude, magnitude of displacement, and that is same as the maximum acceleration. So,
do you want to try to solve this one by plugging the numbers into this formula? Can you do it?
Okay. Do I plug in 3.0 for A?
A right there is the 3 millimeter. So 3 times 10 to the minus 3 should be the maximum amplitude.
I got 355.
355? Really? Omega is 62.8, right? So you gotta square it, and then you gotta multiply 0.003 meter.
Oh.
So that 3 millimeter is equal to 3 times 10 to the minus 3 meter.
I got 11.8.
Okay, good.
so now omega is 6.8 radian per second. And here the amplitude of floor motion near the motor is what? 3 millimeter, which is 0.003 meter, right?
Okay, so you
Plug that
solve this
into
problem. So let me move on to the next example, 14-4. Okay.
Okay. Example 14-4, loudspeaker. The corner of the loudspeaker oscillate in simple harmony oscillator at a frequency of 262 Hertz, middle C. The amplitude at the center of the cone is 1.5 times 10 to the minus 4 meter, and t equals 0, x equals a. First question, what equation describes the motion of the center of the cone? B, what are the velocity and acceleration as a function of time? C, what is the position of the cone at 1 millisecond? Let's just start with the number A. So, amplitude here, already given, 1.5 times 10 to the minus 4 meter, and the omega, angular frequency, is 2 pi f, is 6.28 radian, times frequency is 262 hertz. So that is 1650 radian per second. So with these two parameters, you can define the equation of simple harmony oscillator of displacement function, which is the maximum amplitude times cosine omega t. So that is 1.5 times 10 to the minus 4 meter cosine 1650 t. That's number A. Number B. Now we want to estimate the velocity. We gotta just estimate the velocity and acceleration as function of time. Already I just explained how to derive the formula of velocity and acceleration from the displacement of simple harmony oscillator. So the maximum velocity that's maximum velocity equals omega a. That is formula I derived last session. So that is what? 1650 radian per second times 1.5 times 10 to the minus 4 meter. So that lead to the number of 0.25 meter per second of velocity. Or if you plug them into the formula of velocity of simple harmony oscillator, then velocity should be minus 0.25. So let me just write down the formula of velocity out of simple harmony oscillator. So that is the omega a sine omega t, right? So if you plug the numbers, then that should be minus this omega a itself is a maximum velocity v draw, so that should be 0.25 meter per second sine 1650 t. That is velocity in time. And also acceleration, maximum acceleration should be omega squared maximum displacement of simple harmony oscillator.
So Tatiana, can you come up with a number of maximum acceleration and then find the formula of the acceleration of simple harmony oscillator?
Mm.
Just follow the same procedure like the velocity.
I got
Mm-hmm.
408 meters per second squared.
408 meter per second square.
Mm-hmm.
Okay, then
The equation I got 0.25 sine parentheses 1650 t.
oh no, actually it should be the cosine because the displacement is proportional to the cosine. So the second order derivative of displacement should be just same as the cosine function. So let me just
So omega is 1650 radian per second. You square it and multiply displacement, maximum displacement. So 1.5 times 10 to the minus 4 meter. So maximum acceleration out of this definition is 410 meter per square second. So now if you plug this number into equation of acceleration from the simple harmonic oscillator, then that should be A maximum acceleration times cosine omega t here. This one is maximum acceleration should be defined by omega squared times A. We already just derived the answer of omega squared A. So we just need to plug that number into this formula. Then acceleration in time should be minus 400. Oh, that should be minus sign in front of that. Minus 410 meter per square second cosine 1650 t. Okay. Okay, number C, what is position of cone at t equals 1.1 millisecond? So that's C, now plug this t 1 millisecond into displacement equation of simple harmonic oscillator. So let's plug that. So now formula of the simple harmonic oscillator displacement, then A cosine omega t. So the A is 1.5 times 10 to the minus 4 meter maximum amplitude. And now we're going to plug 1650. And now you plug this 1 millisecond into the t, then that should be 0.001 second. So you plug them all into this formula, then that lead to the answer of this number C question, which is 1.2 times 10 to the minus 5 meter. So after 1 millisecond, this simple harmonic oscillator will have 1.2 times, like 12 micrometer displacement from the starting point origin.
Okay, let's have one more sample problem before we just wrapping up today's session. Okay.
Example 14-5. Spring calculation. A spring stretches 0.15 meter when 0.3 kilogram mass is gently attached to it. That's figure 14-3b. The spring is now then set up horizontally with the 0.3 kilogram mass resting on a frictionless cable. It's in the figure 14-2. The mass is pushed so that the spring is compressed 0.1 meter from equilibrium point and then released from last. Number one, we're going to determine the spring stiffness constant K and angular frequency omega. B, we want to determine the amplitude of original oscillation A. C, we'll find out the magnitude of maximum velocity B maximum. D, we have to also find the magnitude of the maximum acceleration A, max of mass. E, now we will check the PD of the T and the frequency F. And F, the displacement X as a function of time, and G, the velocity at T is the 0.15 second. So we can quickly just draw the picture of this problem. So that helps us understand how the situation actually appears in this problem too. So you have a single spring attached to the wall. That is like this. And there's the object, which is 3.3 kilogram. Attached to this spring, so that the object that is M oscillate along the equilibrium position X equals 0, and that spring produces the power, the force based on Hooke's law, which is X Fx, and that is the mass M produced force downward based upon the gravity. The gravitational force exert downward force, the drag that mass downward, so that displacement X should be expressed in the function in time out of the simple harmonic oscillation motion. So from that, from the given condition of this problem, your X naught is the 0.15 meter, and the mass is 0.3 kilogram. The number one, we have to first calculate spring constant K or stiffness, which is F divided by displacement. So here, F is mg. Only force applied to this spring is the gravity. So F should be placed with mg, and now it goes with the x naught. So here mg is the 0.3 kilogram times 9.8 meter per square second, and x naught is 0.15 meter. From that, speed constant K should be the 19.6 Newton per meter. Using that K and omega, K and mass m, you can find angular frequency omega or angular velocity omega, which is square root of K over m. So plug that K value into the square root, and that should be 19.6 Newton per meter, and m is 0.3 kilogram. That it lead to number of 8.08. In one second. So with using those numbers, you can estimate also magnitude, amplitude of original oscillation. So A is 0.1 meter. Compressed to 0.1 meter, and then C, maximum velocity should be omega A. So omega is 8.08 hertz per second times 0.1 meter. So that leads to the answer 0.848 meter per second. That's the maximum velocity. So number D, question D. So F is ma from the Newton's law. So the maximum acceleration should be force divided by mass. So the force is K times maximum displacement A out of the Hooke's law, and m, that should be divided by mass m. So that is 1.96 K, actually 19.6 newtons per meter, and A is 0.1 meter by that 0.3 kilogram. So the answer is maximum acceleration should be 6.53 meter square second. And E, the period T is 2 pi square root m over K. So here 2 should be 2 pi times more square root of 0.3 kilogram, and denominator should be 19.6 Newton per second. So that should be 0.777 second of that period, and the frequency is, as you know, 1 of t. So that frequency is 1.29 hertz. And now F is asking the displacement x as a function of time. So motion begins at point of maximum compression. T equals 0, x is minus a, which is minus 0.1 meter. So x should be minus a cosine omega t. Here, cosine theta. So basically, here t is 0 and x is minus a. Pitch is minus 0.1 meter. So basically that lead to that displacement equation like this. So the cosine theta should be minus cosine theta minus pi. And if you move that minus sign to left hand side, then minus cosine theta is same as cosine pi of theta. So basically that is same as cosine theta minus pi. If you apply this relationship, this formula, then x should be minus 0.1 meter cosine 8.08 t. So you plug the minus sign into this cosine function, then that should be 0.1 meter cosine 8.08 t minus pi. So that the initial phase value should be either minus pi or minus 180 degrees. The question G, we have to estimate the velocity at 0.15 second. So all we need to plug that the number of time into the velocity function out of the displacement equation. So that is V is first derivative of displacement in time. So that is omega A sine omega t. So we plug all this number omega and the maximum displacement A, and again the omega plug back into this formula, and then replace t with the 0.15 second. Then velocity should be 0.808 meter per second sine 1.21 radian. So that leads to the answer of G, which is the 0.756 meter per second. Okay.